If there are any problem with that you cannot see the slides or something like that, or cannot hear me, then please let me know. Okay, so also now we got more persons they joined. So yeah, then let us start with the class. So yeah, welcome to the introduction to the advanced mechanical and electronical system engineering. So today is class 7, when it's the turn from Professor Imura and from me to introduce our research. And so yeah, maybe let me start with mentioning what is the assignment. I think Imura Sensei has a similar assignment, but please listen to his instruction carefully. So for the first half, so for the one my part, the I would like to ask you to write a short report, just about 100 words, of course, written in your own words. So was very similar ones. So please write a report about what I'm going to speak. There will be some, it will be posted on MS Teams, and the deadline is by next Wednesday, the 12th November. So by or on 12th November. So please submit it then. So yeah, it's a form where you have some possibility to write a short text. So please use that and submit then the text. And then, yeah, as you all know, as you're joining this class, so this half year is given remotely, but the second half will be given in the classroom. So please be ready to go to the classroom after this class, after this half. So there will be sufficient time for you to change the location. I will make sure of that. Okay, so some student already left. Let me block the attendance again. So, okay. Then let us start with the introduction of my research. But before that, let me give you a short introduction to my career. So I, as you well know, maybe mostly I'm from Germany. Most of you can guess by the accent. And to be more precise, I was born and grew up in Aachen, that's some city in Germany. Then after that, I moved to Wuppertal, another city in Germany, not too far from Aachen, where I started to study mathematics. So actually, I'm not an engineer, I'm a mathematician. And this I studied in autumn 2005. I graduated in 2010. This was a degree including the master. So in Germany at that time, we had some combined bachelor master degree, also called diploma. And then I continued with my PhD studies, also in mathematics, which I then finished 2015. And then I continued with a postdoc. So I was quite interested in staying in academia. And then it's expected that you, after the PhD, continue with some postdoc. So usually you don't find a permanent position immediately. Instead, you work on some short-term contracts. And I had the opportunity to work on a postdoc for 3 years at the department of at the mathematics department at university in Gothenburg. To be more precise, it was 2 universities combined. And after that, I started to work here at KUAS. So I'm already since 6 years here in Kyoto. And yeah, as you will know, I'm here a lecturer. Okay, so as I already mentioned, actually I'm not an engineer, I'm a mathematician, and to be more precise, my research field is complex analysis. And there I would like to point out that the name is actually not referring to the word complexity. It's maybe something it's complex, but actually it has nothing to do with complex in the sense of complexity. Instead, it is called like that because it is working with complex numbers. And I'm pretty sure you are very well known with it, but still let me shortly recall what that is. So much about my career track as a course introduction. So what are complex numbers? So the first paragraph is just copied from the slide before to make it easier why I'm speaking about complex numbers. So I want to discuss some approach that is not so popular to introduce complex numbers. Maybe that's something new for you to hear. So if you think about having a piece of paper and you flip it twice around some axis. So if you flip it twice, then you see, of course, the same front page of this again, isn't it? So you see the same page again, the same side again. And now I would like to combine that with mathematics. So let's think about that flipping is something like multiplying with -1. So if you think about the thin paper corresponds to the real number axis, then by flipping it, what we do is we turn it around on some axis, here represented by 0, and then we are making the 1 to -1, the 2 to -2. So this corresponds like multiplying with -1, like a half gets flipped to -1/2, isn't it? And so the procedure of flipping it twice, this corresponds then like multiplying with -1 twice. But that is, of course, so taking the product with -1 twice is like -1 times -1. So this is 1. And this is what I said before. So we actually do not change anything. So this rotation, this flip, is now the same like multiplying with 1, which corresponds to changing nothing, isn't it? So, okay. Now, the question that I some kind of have for you is what can we do twice to get one flip? So, of course, in the picture, it's clear what we're doing is something like a half flip. We turn it by 90 degrees. But if you think about this mathematical representation, multiplying with a number, then it's actually then the question, um, which number can we take so that if we take the product with itself, we do not get 1, like this double flip. No, we want to get just one flip. We want to get -1. So we want to have that the square of this number is equal to -1. And as you well know from high school or junior high school, there is not such a number in the real number line. And since such a number doesn't exist, mathematician created one, the so-called imaginary unit I, which is defined by the property if you square it, then you get -1. In engineering, especially electrical engineering, I think it's very common to use J to not mix up the I with the current. But this is just a symbol. So still what we mean by that is the imaginary unit, which is defined by this equation. If you square it, then you get -1. Okay. So this is the one, and now the complex numbers is now taking not only the imaginary unit, now also consider any multiple of that, like 2 times I or 3 times I or half I, something around here. And also you can combine it like formal addition, or as a pair. You can also see it with a real number, like we have here the example 1 plus 2i, which is then corresponding to the number in the plane 1 plus 1, 2. Sorry, yeah, not the number, the pair 1, 2. And originally, actually, complex numbers were introduced to solve polynomial equations. So this was done in the 17th century or something like that. So several hundred years ago. But since then, there are many applications of them. Sorry, to be more precise, the imaginary unit was introduced a few hundred years ago. But since then, there have many applications of them appeared. So I'm pretty sure you all have encountered that. Important example is, for instance, the computation of alternating currents, but that is just one of many examples. Okay, so much as an introduction to the complex numbers. Let me continue with the complex analysis. So what is now the idea behind complex analysis? So the idea is to take the complex numbers and now use them like we did with real numbers to get calculus. And so what we just do is we copying more or less the notions. So at least at the beginning, we're copying the notions that we know from the real setting. That means with respect to real numbers like integration or derivatives and so on. And we transfer it to the complex one. And let me give you an example for that. So if you have a real valued function f, then we call that one differentiable if we can approximate it, at least locally, by linear functions. To be more precise, if we think about that we have our function f, then we can write it as f of x is given by f of xo plus a times x minus xo plus some reminder, where the reminder vanishes in a good way. So if we can write our function like that, then we call it that it's differentiable in xo. So we can write it as a constant part plus a linear part plus, as I said, this reminder. And actually, in this case, then the derivative is just this number a here showing up. We have here as one factor. So this is only a local approximation. So the reminder usually just getting small, close to xo. But so this characterized differentiable functions quite well. Especially we can copy that one now to the complex setting. So now we consider a function where we can plug in a complex number and get the complex number back. So we call this one then complex differentiable if we can write it more or less like here above, like f of zo plus a times z minus zo plus some reminder. So now here the a is a complex number, so that's some advantage that I didn't recall, but we cannot take here the product of a and z minus zo. So for complex numbers, and so this is how if we can write f like that, then we have a complex differentiable function. And in this case, a is a is the complex derivative of f. Okay, so you see we took the real definition or real characterization of differentiable and you just copy that to the complex one. So we haven't changed much, but actually it turns out that it's a quite big change. So even though we did not change much in the definition. We just some kind of translated everything to the complex setting. So actually, it turns out that this notion is now much more stronger than actually real differentiable. For instance, so important property that I want to mention that complex differential function have that they usually do that real differentiable function do not have, we can always write it as the sum of two harmonic functions. So the real part is a harmonic function, and the imaginary part is also a harmonic function. And as you might well know, harmonic functions are quite important. They show up in many physical systems like heat, pressure, and electrical charges. And actually, to some extent, also complex differentiable function shows up. So let me give you a more precise example for that. So let's think about it. We have here a field, an electric static field of two charges, plus and minus, for example, but actually doesn't matter actually. Then in this picture here, we have green lines drawn, and these green lines are the level sets of the electric potential, which itself is a harmonic function. Okay, and then blue, I have drawn the flow lines. So how some third particle would flow, for instance, if it is positively charged. Then of course it would be attracted by the negative charge, so it would flow to that. Okay, so of course, so this picture is in the plane, so we are talking here about some electrostatic field in the plane. If we would have so this is some kind of only in 2D. Okay, but now actually we can find some harmonic function V whose level set is actually also the blue lines. And it turns out that if you combine this potential, the electric potential, with this flow function, let's call it like that, or stream function, like we did it here, then we get that this will be a complex differentiable function. So here you see that complex differentiable function shows up even in some physical systems. There's just the major restriction that this only works in the plane. Okay. So this is some kind of introduction to complex analysis and how we see it's already different from real analysis. Okay. To explain a little bit better what is actually my research, I need to introduce more notions. So one tool that I'm working are manifolds. So this is an important part of the complex analysis. To study complex manifolds, it's also called complex geometry. And a simple example for such a complex manifold is the sphere. So I mean the surface of some ball. So this is a complex manifold. And so actually, this is just one example. So there are many, many more, like this word manifolds indicate. And so the point is still it's a good reference because we can think about that the sphere is like that we have several papers that we glued together. Like we can think about, we cover our sphere with maps and then we can glue them together and then we get our sphere. Okay, and so yeah, like you have some papers and then you glue them at some edges together, at some at some overlap together. So this gives you you can do that to construct the sphere by this gluing together. And now the point is that actually the screwing procedure, if you can do that, or by doing that in more complicated way than just for spheres, you can get some kind of any kind such object, many kinds of other objects. And so these are complex manifolds where we not only glue together the plane, maybe also higher complex dimensional spaces. Okay, so another example for such a manifold, a complex manifold, is a torus, the surface of a donut, like we see it here. And of course, we can see that this one is quite different than the sphere. But there are much more complicated examples, and for instance, they are used in theoretical physics, like string theory. Okay, like we see, so this is actually just a projection of the complex manifold, but yeah, this is one example for such a manifold used in string theory. Okay, so this is complex manifolds, and now, as I said, we want to study them. And to do that, we're actually using vector bundles. And I don't want to introduce the full notion of vector bundles. Let me just restrict to the important case of a tangent bundle. So the tangent bundle, that is a vector bundle which contains all the vectors which are tangent to the manifold, like we see here in the sphere. So now the tangent bundle depends on the point that we are. For instance, like at this point here, then we see that there's a whole plane of vectors which are touching or tangent. Oh, sorry, the plane is touching the sphere, and then all those vectors that are tangent. So therefore, it's a tangent vector, and we call that the tangent plane. And now we consider it not only for all points, we consider it for all points, or not, sorry, we not consider it only for one point of the sphere, we consider it for all points of the sphere, and then we get the tangent bundle. And I'm sorry. And now our vector field is that we not pick all the tangent vectors, we only pick one per point. So that corresponds, yeah, that's maybe nice explained with this picture here. So here, for instance, we have chosen the tangent, the vector field where we go straight forward to the south. So in each point, we pick the south vector of some certain length, and that we do everywhere except in the north and the south pole. There's of course not possible to choose a south vector, so there we just pick the 0 vector. Here in this picture, we picked the vector where we go to the east. And again, this is not possible to do at the north and the south pole, so there we go pick again the 0 vector. And here we have also the picture, sorry, some vector field on the torus, the same procedure like above, just going to the east in some sense. So this we can do now everywhere. There's no restriction because there's no north or south pole here. Or here, the analog to that, where we always pick the one which is so if you are some kind of outside of the donut, we are going to the south. If you're at the top of the donut, we're going outside. If you're at the bottom, then we go inside. And if we are and if we are inside at the donut, then we're going to the north. So we're going some kind of around circles, in the sense like we're picking up vectors in this direction. So this is also a vector field, and here it's remarkable again that we do not need to pick any 0 because we do not have this exceptions like here with the north and south pole. That it doesn't make sense to go to the south if you're at the north pole, because then we have too many directions to go. There's not one choice. And so actually, as this example already shows, the geometry of the manifold gives us now some abstraction on what kind of vector fields exist, some kind of on this manifold. And an important example for that is the so-called Harry-Bohr theorem. So on the sphere, it's actually not possible to find a vector field which does not vanish at least on one point. Or you can also express it, we cannot comp a hairy ball where the hairs corresponds to the vectors flat without creating a cowlick. A cowlick is, like we see here in the picture, it's a point where we have zero. So this is a property of the sphere, this Harry-Bohr theorem. But as we can see in this example given here, this is not the case for the torus. So the torus do not have this property. On the torus, we can easily find vector fields which are vanishing. There are some other properties for the vector fields on torus, but I don't want to discuss that. So that is, well, but this is a great example for how the geometry of some sphere gives us some abstraction on the vector fields that are defined, and of course the other way around. So by having found such a vector field, we know that the torus is not comparable to the sphere. Okay, so this is a motivation why to study the tangent bundle or vector bundles on manifolds, since they are helping us to understand the massive manifolds quite much better. Okay, so, but unfortunately, this is still not sufficient. So actually, if you study complex manifolds and vector bundles, then you are soon encountering some limitations. So you need to consider more general objects. So they are called complex spaces and sheaves. And let me just maybe mention, so complex space can be seen like that we have ramifications. So we have not only deformation of a plane, no, they are more complicated to glue together if you want, like we see it on this one here. And vector bundles are some, sheaves are some kind of more general version of vector bundles in a similar fashion, but that's getting a little bit too much. And so now what I can mention is that, so now we are at the notion that some kind of, on the level of notion, where I can speak a little bit about my research. So I, with my PhD advisor, John Rubenthal, we studied the sheaves on some complex spaces and how they change under modifying the complex space. So if we deform it in some specific way, how does the sheaves behave? And based on that, I could generate some work from some Japanese professor here in Kyoto. So he then proved it for manifolds, and I could generalize it to complex spaces and sheaves. And so that is some kind of interesting for classifying what kind of complex spaces can exist. And then later during my postdoc time, I worked on that. I generalized, or sorry, not I worked on this also with some collaborator from Sweden, Håkan Samuel Kahn. So he gave a criterion. So we gave a criterion on actually, if you have a complex space, we do not have, we assume it's from the beginning it's a complex space, and we know that it has some certain property. The tangent bundle has some certain properties, then we already know that this is actually not having such ramification. We know it's already a manifold. Okay, so this is some kind of introduction into my first part of my research. But actually, yeah, it's in some kind of different direction. Also to study complex manifolds, I also studied metrics. And so if you think about a vector bundle, for instance, a tangent bundle, then we can maybe, if the manifold is embedded in the space, and we know what is the length of a vector, but for more complicated manifolds, that is not so clear. And so what you do is you introduce a measurement for how long a vector is. And so this is called a metric. And so now the curvature properties of this manifold is actually also represented or characterized by the existence of some certain metrics with positivity properties. So, for instance, if our metric is positively curved, then we get information about, if the metric behaves in a certain sense, then we get some information whether it's positively curved like the sphere, whether it's flat like the plane, or if it's negatively curved like the saddle. And this is closely related to whether you have, what kind of triangles you have. So the triangles here are all respect to the shortest length on the sphere. So how we can go from fastest from this point to this point here. But then we see that the angles if we take a look on triangles on the sphere, that we see that the angles sum up to something greater than 180 degrees. So on the plane, we know that the angles always sum up to 180 degrees or pi. And we see for the sphere that this is not the case. So they're getting greater. And if we have something negatively curved, then we get something smaller. So the angles are here smaller than the one in the triangle. So the sum becomes smaller than 180 degrees. And but the problem is, so even though this is very fruitful to understand manifolds, there are many examples where such kinds of metrics, which would give us information about the curvature, do not exist. And so it's quite restrictive to assume that such a metric exists. And then the trick is to consider metrics which are singular, in the sense like they are having some vectors are allowed to have the length 0, even though they are not the zeroth vector. So such singular metrics were studied by other collaborators besides of my PhD advisor from Gothenburg. So Richard Lerchen, Hossein Raufy, and John Rubenthal. We studied them, and so we were able to calculate some terms related to the curvature for such metrics, and this could be improved further with Elisabeth Vulkan, another collaborator from Gothenburg. Okay. And let me use the last 5 minutes to speak about my research plan. Very costly, of course. So on one side, I would like to continue my research by working on the project, as it's also supported by the Kakenki grant. For instance, in collaboration with some collaborator from Osaka, Takayuki Koike, and my former colleagues and collaborators, I would like to investigate the existence of the matrix. So as I said, we cannot avoid singular matrix, but maybe it makes sense to take a look on matrix which are not too singular, so-called minimal singular. So trying to minimize the singularities that they have. On the other side, of course, I would be happy to work in interdisciplinary projects like at Kurs. Also, then it's a problem that my results cannot be applied directly. So that's a problem with often with pure mathematics, that it's not quite straightforward how to apply that straightforward in the directly, even so it shows up afterwards often. So still, I could maybe offer some analytic method or insight into mathematics. And let me give you an example for that. So where some kind of pure mathematics is also in the can be found in engineering. So one algebraic geometry is an important field in mathematics, which is quite related to complex geometry. Actually, this can be used in statistics, so-called algebraic statistics, by using very high dimensional spaces where the dimension corresponds to the degree of freedom, some kind of. And so this can be used to understand the behavior of gases. So that's quite interesting in statistical mechanics, and that might be interesting in a collaboration with Nakamura Sensei. But unfortunately, that is not so easy to start with, so that hasn't started yet. But yeah, still there's time. Okay, so then that's actually for all from my side. So thank you very much for your time and attention. And yeah, if you have any questions, I'm happy to hear it. If there's no question from your side, then let me maybe point out with the so there it is. Let me mention again the assignment. So please write now a short report about this part of today's class, around 100 words. I agree with you that this might have been difficult to follow, so it was just a short introduction to especially the latter half into my research field, which is rather difficult to describe. So, but I'm pretty sure that still you were able to catch some part. So that shouldn't be a problem for you to write such a short report. So please submit it by next Wednesday. And then, yeah, let me close today's half, the first half. And let me ask you then to continue in the classroom when Imura Sensei speaks about his research in the room S311, on the third floor, room 311. So yeah, please then continue there. The scheduled time is 5:05. So great. And thank you very much for your time, and then have a nice evening.
Thank you, Doctor.
Thank you.
Thank you. Goodbye.
Bye bye.